Thank you very much for the invitation. So I apply the principle to start at the time I was given, so which is 10 minutes ahead of the formal time, just to be sure that I will finish on time. So my lecture is, first of all, I thank the organizers for the invitation. So my lecture is a lecture by a geometer. So of course I will be mostly interested in the interactions of mathematics with general relativity, and because it's some kind of a historical moment for the theory of general relativity, I took the point of view of having a historical approach and try to look at a number of things in this perspective. Second point I want to make is I'm a geometer, as I said, and there are many other ways in which general relativity interacted with mathematics. In particular, one way which for me has been really amazing in developments is the numerical aspect, which have developed very spectacularly. And I think from that point of view, of course, I will not say anything, not because it's not important, just because I'm not competent to speak about it. So anyway, so as I said, the outline of the lecture will be just to put things in perspective. So it is a very obvious, trivial statement to say that geometry and physics have really a long history in common. And actually, really, in particular in the 19th and 20th century, a large part of theoretical physics has been extremely closely related to the developments in geometry. And so actually, in the case of general relativity, it's really extraordinary, the extent to which this has happened, and I want to discuss it. And of course, I could have given many other examples, but if you look at the program, a number of speakers will be the most qualified people to speak about these kind of interactions, and particularly the new results which have been obtained recently, and some of them absolutely spectacular. I could even dare to say almost unthinkable. So I think I will skip that in a way. So what I want to talk about, so this is the listing of things I want to cover, is say a few words about the prehistory of general relativity. I want to spend some time on Gregorio Ricci Cobastro, because I think he's a figure which has been underestimated, whose influence has been underestimated, I feel. And also, I want to say a few things on the birth of Ricci curvature, which, of course, for all of you is an obvious notion. Now, I want to just come back, but for all of you, it will be a triviality, but it will be an opportunity for me to set up notations, the giant step of general relativity. Then I will comment on Hermann Weyl's attempt in connection of unification of general relativity and electromagnetism, which has had a fantastic impact on the development of conformal geometry. And then speak a little bit about Kaluza-Klein theory, actually strictly at the Kaluza level, and in which way it was really in a nutshell, the possible development of what has been developed later on as bundle geometry. But that's a typically missed opportunity. It took 50 years to do it, actually. But it's interesting to see how it happened. Then I want to point to some article by Cornelius Lanxos just before the war, and the Second World War, and which is also a very interesting instance of difference in points of view between mathematicians and physicists. So I would like to highlight this. And then I will come to in which way the ADM approach, which has been already very central to the presentation by Professor Wald, as really, from the mathematical point of view, being extremely important for a number of developments. I will say a few words about supergravity and killing spinors, which has also been a very interesting moment. So these are the topics I would like to cover, put them in perspective, and again, don't misunderstand me. Of course, I'm very much aware of a number of things which will be discussed by really the people who have been shaping mathematical general relativity in the last part of the 20th century and the early part of this 21st century have even more important developments. But I felt I leave it to them to explain what they've been doing. So I'll skip that, but not because it's not important. Actually, it's even more important than what I'm going to talk about. Anyway, so let me go back very quickly to what I call the prehistory of general relativity. And of course, the very, very important development in geometry happened after this very major discovery by Gauss of the possibility of having intrinsically curved spaces. So, and then the next development, which was, of course, the case of surfaces. Of course, extremely important development because this was a completely new notion which didn't exist before. And the next development was, of course, Bernard Riemann habilitation on June 10th, 1854. Never published while he was alive, but still there is a document afterwards. It's very interesting if you read the document itself, so assumptions on which geometry is based, that clearly, as you know, I mean, it was processed in the typical way these things were done, so he had to present his research work, but also the faculty would suggest some themes, and then he had just, I think, 2 weeks to, because the choice between the 3 themes was done almost last minute, as it's traditional to do. And Gauss, who was in the jury, chose this topic of assumptions on which geometry is based. And it's very interesting to see that in the document, actually, which is, of course, very important for the development of geometry, contains also a discussion of really things which have to do with physics. And he really mentions very, very explicitly his own reflection on space. And for him, space in the physical sense. And for him, space, he's talking both about the very large and the very small. So it's very interesting that this notion of scale is very present in Riemann's thinking, and which shows that all the developments he was doing, which was really strictly mathematical, was very much inspired by his own reflection on physics. And actually, it's quite clear that at that time he was trying to come up with some possible models for ether, and this was really very, very important. So, in a sense, it's also interesting to see, and which was also present in Lobachevsky's development about new geometry, to try and introduce some ideas that maybe through measurements one can do some things. And for example, Lobachevsky takes great care in his article about, non-Euclidean geometry, that although all measurements we have made don't show any evidence that the space is curved, but so it's clear that at this time for these people who were outstanding mathematicians, in particular for Riemann, keeping in mind, thinking about physics was extremely normal and quite important. Anyway, so next one I want to point to, probably it's known to many of you, but I think it's so extraordinary that I want to quote him, is some work which has been done by William Kingdom Clifford. And Clifford is also a person, well, in the same way as Riemann, died very early, as Riemann from tuberculosis. And actually he was also, as Riemann, weakened for part of his life, although it was a short life, by illnesses. And he had a note which is very, very extraordinary, so very visionary. So here I quote his note on the space theory of matter, and which is to say, I wish here to indicate a manner in which these speculations may be applied to the investigation of physical phenomena. I hold, 1, that small portions of space are in fact analogous to little hills on the surface, which is on the average flat, namely that the ordinary laws of geometry are not valid in them. Second, that this property of being curved or distorted is continually being passed on from one portion of space to another after the manner of a wave. Third, that this variation of the curvature of space is what really happens in that phenomenon which we call the motion of matter, whether ponderable or ethereal. that in this physical world, nothing else takes place but this variation subject to the law of continuity. So of course, it's not yet a theory, it's just some kind of considerations, but in a sense, the very basic concept, which will be at the base of general relativity, is so much visible in this document that it's very remarkable. It's 1876, so quite early. And anyway, so I wanted to point to this because it shows in the case of Clifford, who played also a very important role in had a really very substantial mathematical contribution, that also, I mean, thinking about connection between geometrical representation of space and physics was very much in his mind. And then last comment about the prehistory of general relativity is, of course, this 1905 introduction by Albert Einstein of special relativity. And as you know, I mean, clearly his basic thinking was very much influenced by trying to come up with a good interpretation of the results of the Michelson-Morley experiments. And in particular, the fact that really what one has to take seriously is the fact that the speed of light is an absolute. And therefore, he makes some developments, discusses a number of issues on this. In particular, he shows that it has consequences on what one thinks of simultaneity, on synchronization of clocks, and so on. And it's very interesting to see that two people took up these very fundamental new ideas introduced by Einstein. Two mathematicians, Henri Poincaré, so we are here in a good place to mention his name, and Hermann Minkowski. It's very interesting to see that the developments by these two people about what Einstein had been introducing are very different in spirit. And it's interesting to see that, so in the case of Poincaré, the article was published in the Proceedings of Palermo, and the title is Le Mouvement de l'Électron, the movement of the electron, and he's discussing this really from a mathematical point of view, but still in the style which is very much that of theoretical physics in a certain way. And at that time, and the way he discusses it is by putting a lot of emphasis on invariant theory. So he shows that the transformation, which are quite important in Einstein's discussion, the so-called Lorentz boosts. If you think of them as mathematical objects and look at the group they generate, the group they generate is a group of invariants of a metric, of a generalized metric, which we all know now as Lorentz metrics. And so a metric of nature 1, 3. And so it's very interesting that his approach is that of invariant theory. At that time, invariant theory was really dominating a large part of mathematics, so it's not so surprising. In the case of Minkowski, actually his famous article, Raum und Zeit, was the result of a quite public lecture, but this is really in such an article, which is really meant more like in the style of Euclid's Elements, as really a very basic investigation into mathematical structures. And so he really very emphatically speaks about space-time and really thinks of this as a new geometry. So of course, mathematicians had been also considering bilinear forms or metrics in general, but the fact that there should be a very systematic study of this type of geometry, which are not positive definite, but with a signature 1, 3 or 1, n in n plus 1 dimensions, was really clearly, stimulated very, very strongly by the fact that it was physically relevant in the approach introduced by Einstein. So, of course, it shows that next to Riemannian geometry, there should be also consideration given to more generalized geometries. So this was why I wanted to mention this prehistory of general relativity. So now about Gregorio Ricci Corbastro. So actually, I want to mention him because, of course, Riemann clearly understood everything he did. And although in his paper there is only one formula which describes the expansion of a metric in the neighborhood of a point if you take normal coordinates in a way which introduces the leading term in the perturbation as being the curvature. But it doesn't tell you how you compute the curvature. So, of course, he knew how to do it. But as you know now, the way we present the whole thing is there is an intermediate object between the metric and the curvature, which is a covariant derivative. And therefore, this object was implicit in Riemann. Actually, there are some documents by Riemann, particularly a prize submission that he made to the French Academy, in which it's quite clear that he has an understanding of some of that. But the only place where it was really presented systematically is really in some articles by Ricci, and although we tend to call the coefficients of the covariant derivative with the name of Christoffel, if you look at what Christoffel had been doing, of course he introduces the Christoffel symbols, but in a way which is kind of very implicit. He is interested in the question of how, if you take two metrics or the same metric you express in two coordinate systems, how do you get about computing, in particular the curvature? And then he notices that there are some expressions which appear so often that it's worth giving a name to them. But it's not clear that the true meaning and the true value, mathematical value, is actually has been understood by Christoffel. Although he sees the value because it's so important to make computation. So actually, really in a very important article which was published in 1888, this idea of an absolute derivative, now we would call it the covariant derivative, of course, is developed by Ricci in a completely conscious and systematic way. And of course, this goes on in the further articles, which I'm going to show in a minute, in the Bulletin des Sciences Mathématiques, which is even actually very remarkably written and still quite modern language. And of course, the typical reference paper, which is quite often given, is this very systematic presentation of a méthode de calcul différentiel absolu et leurs applications, submitted in 1900 in Mathematischen Annalen. I always quote this. It's interesting to see Italian mathematicians publishing in a German journal an article in French. So it shows that times are changing. So I'm just giving my lecture in English now. Anyway, so but this, if you never looked at this document, it's extraordinary. If you don't know the date, you could believe it has been written just last year. It's absolutely fascinating because, in particular, they contemplate all domains in which this kind of geometry is relevant, and in a way which is quite very impressive. So here is some quotes of this, the one in French in the Bulletin des Sciences Mathématiques, which in some sense was related to Institut Henri Poincaré at some point, so I thought it was a good moment to quote it. And again, very systematically presented and very interesting. Anyway, so this was, of course, my whole point is to say that, of course, the key element in Riemann was the introduction of the Riemann curvature tensor. And then one thing that Corbastro did in 1904 was to introduce in an article in Italian, direzioni in varianti principali in una varietà qualunque, some kind of a piece of the curvature, which we now call, of course, the Ricci curvature. But it's very interesting, the motivation. The motivation of Ricci is completely geometric. And you are in a situation where on the tangent space of a manifold, you have the scalar product, a metric. And then you using, the construction which I just repeated there, you can also think of this as a contraction of the curvature tensor, which you can do it intrinsically without using the metric. Then actually you create a new bilinear form, which you can prove is symmetric. And then the key element is to say, well, after all, if you have a bilinear form in presence of a non-degenerate scalar product, then you can diagonalize, transform it into a linear map, and look at the eigenvalues and eigendirections, which means that in a Riemannian manifold, you have, in a very natural way, some very preferred directions, which are the eigendirections, eigenvectors of Ricci. this new object, which is the Ricci curvature. And of course, this is completely natural. It connects very directly. In the case, if you're looking at the hypersurface in Euclidean space, you actually recover this way, but if you remember the formula which links the second fundamental form and the Ricci, you actually get exactly the principal directions and, of course, a very direct formula for the principal curvature. So in a sense, it completely generalizes the principal directions for a hypersurface, but for any Riemannian manifold. What is very remarkable, so this is very natural, looks a completely reasonable thing to do, but as far as I know, there is not a single mathematical theorem which came out of that. So in a sense, it was very natural to introduce the Ricci curvature, but the motivation for which it was introduced actually failed. And so, of course, as you know, Ricci curvature has had a lot of further consequences. So this was basically what I wanted to say on the Ricci Curbastro, and now I move to general relativity. So of course I will do it very quickly because you're all experts in that, so I'm not... but one thing I want to do, because I know that this infuriates usually physicists, so it's good to provoke people from time to time, which is to say that there is this famous two papers back-to-back by Marcel Grossman and Albert Einstein, 1913, in which basically the foundations of general relativity are posed, except, as you know, that the field equations are just incorrect, and they are incorrect very deeply, actually, which is kind of surprising with the people. But still, if you think of this from the purely epistemological point of view, the key point is that the big shift, which is moving in Newton theory from the gravitation being derived from a potential, which is a scalar function, to really using the metric as the potential, is such a fantastic leap that actually, of course, maybe they missed the field equations, just a small thing, of course, but it's just there. And of course, you can imagine that maybe they couldn't do it right away, but it means that you can really expect. And of course, this provides as a right framework the idea that really one has to go from Minkowski geometry, which was the setting of special relativity, analog of Euclidean geometry, to now something which will be in the same way as you have Riemannian geometry next to the Euclidean geometry. Now you have also Lorentzian geometry as an analog of Riemannian geometry, which is exactly what is proposed by Grossman and Einstein. So I think these two papers are still very interesting to read, even if, of course, it's not the final word, and you needed some more steps. And, but in a sense, these two articles clearly show that the Ricci curvature has to enter in some way, still missing the right way, but I wanted to bring up to attention, because I think it's still interesting to read these two papers. Anyway, so I'm now moving to, of course, the key big step, which was 1915. That's why we are celebrating 100 years of general relativity, after intense correspondence between Einstein and Hilbert. And of course, as you know, the new idea was to derive the field equation from Lagrangian, which is, as you know, the total scalar curvature. And of course, what is very, very interesting, if you look at what Hilbert has been saying about this, in the sense he looked at, his reasoning is, suppose you want to involve the geometry and you try to do it in the most natural way, in the simplest possible way, and that's the way he comes to the total scalar curvature as the Lagrangian. So it's done, again, in a spirit which has to do with the invariant theory. That is, you look at really what could be the simplest way of deriving things. So, of course, get the Einstein equation with the left-hand side completely geometric, with the Einstein tensor, Ricci minus 1/2 scalar curvature times G, and the right-hand side, which concerns the rest of the physics, the stress energy tensor. And of course, I mean, the key point now, since you have the field equation, is to solve them. And I know it has been the business of many of you for many years, and it will still be, there's still plenty of questions to be discussed. From the strictly mathematical point of view, as you know, this set of equations is a very difficult one. let me recall the unknown is the metric. T is really supposed to be given to you by a good description of the physics. But even coming up with a right way of formulating T, I mean, which contains the physics, requires also some geometric thinking and is non-trivial in some way. So so this is everything of this nature is well known. So let me try to see that, because it's remarkable how quickly, although it was a fantastic as I said, a fantastic leap, a giant step, that some people were able immediately to get some very substantial developments. So, of course, you have the Schwarzschild solution, which came very quickly. You had a number of people who were able to grasp this, although it was, at that time, really forefront mathematical research. And one of them is Hermann Weyl. And so 1917, so just, as I said, extremely quickly, Hermann Weyl made a first attempt to unify further physics in trying to propose a theory which would bring together gravitation and electromagnetic theory. And what is of interest to me, of course, it was also that at that time, just because of, it was mentioned by Professor Wald, that if you want to put electromagnetism in phase with gravitation, you are facing other gauge problems. And actually, this question of gauge theory, as electromagnetism is, you really further forces you to really have a further reflection on the geometric content of the theory. And actually, it's very interesting to read Hermann Weyl's contribution to this, and because it forces you to go away from the, I mean, to really look at the covariant derivative in a broader sense, and actually to think of that quite, not only in a metric context, which I think is very important. And of course, the way he was introducing a new parameter, you need, in order to unify gravitation and electromagnetism, you cannot rely only on a metric. You need some other field, and the field is a scalar field. It's a function. And this function, the way he uses it is just by putting what one now calls a conformal weight to the metric. And of course, this really brings another geometric theory under the spotlight, namely the theory of conformal metrics, that is, metrics up to a multiplication by a function. And of course, in this context, when I say metric, I'm covering both Riemannian and Lagrangian. I want to be able to cover the physics, of course. And so this is the way Hermann Weyl is discussing this. And in particular, because of this, it forces him to get into what is actually invariant, what is invariant in the geometry of these objects, which are conformal classes of metrics. And he discovered on this occasion what one now calls the Weyl curvature tensor, which is remarkably the complementary part within the Riemann curvature tensor of the Ricci tensor. So if you know the Ricci, if you know the Weyl, you know the full Riemann curvature tensor. And it's very remarkable how this happened. Again, that general relativity, or more specifically, the interest for people to unify general relativity at other parts of physics, here electromagnetism, really prompted people to understand a wider class of geometric objects. And so this is quite remarkable that the theory of Riemann with the Riemann curvature tensor with these two components has been covered. First, I mean, the stress has been put on the Ricci tensor by the Einstein equation, and then when you want to broaden the scope and include electromagnetism, then you get the other, I mean, you have to look more carefully at the other part of the curvature. Okay, so this was, so now let me speak a little bit about Kallu-Klein theory, and which again is another attempt to unify electromagnetism and general relativity. And so it's 1918, so again, a very, very short time. It's interesting that Kallu wanted to submit an article in which he was proposing another approach to to unifying the gravitation and electromagnetism. It's remarkable that when Einstein got this article, he was very skeptical and more or less refused publication for some time. I got hold of the cards that they exchanged at this occasion, in which Einstein said, well, I think what you propose is fine, but I don't see why it would be interesting, and therefore was not supporting publication. Finally, he changed his mind, and it was published in 1920. But it's interesting to see, so what was the idea? And I'm sure you all know that. So the idea was to say that maybe space-time should be enlarged, and you should think of a product of a usual space-time, four-dimensional, with another variable, which will be more or less the physical space in which electromagnetism takes place. So you are now considering a five-dimensional space-time, enlarged space-time, with a very natural projection on the usual space-time. And the key point is that, of course, you have various data to work with. So you have this projection from the five-dimensional extended space-time to the usual space-time. You have the metric downstairs on the usual space-time. Then you have an extra variable, which is, I called it U in my notation here, which is the R variable. And then you have also the usual electromagnetic potential, which is a one form on the base space, M, that you can lift to the total space. And then the ansatz, the so-called Kallu ansatz, is just to write the metric on the five-dimensional space the way I wrote it, so I don't want to read the formula. But of course, the key element was the computation done by Kallu to compute the Ricci curvature of this five-dimensional metric, and the fantastic, so from all the data, and the fantastic feature is that if you insist that you are writing the vacuum equation from this five-dimensional metric, then you actually get usual Maxwell equations on one hand, and you get also the the right coupling between the Einstein equation and the gravitation and the electromagnetic field. So the Einstein-Maxwell equation. Actually, I should be a bit warn you, because you see I've put in front a certain function phi, which more or less tells you what is. It's more or less like introducing some kind of scale for this electromagnetic variable. I don't know how to call it. I mean, this extension of the space. And it's true that if you look at the general equation, looking phi as a function, then of course you get more complicated terms and you don't know exactly how to describe it. And of course the right normalization is to take actually phi equal 1, but then it leads to inconsistencies. So actually this idea was a fantastically productive idea, which has come back in theoretical physics many, many times. Kallu, Klein has died and was reborn a number of times, each time with some kind of problems, difficulties. But what is very remarkable is first of all, this content of the fact that it delivers for you, looking at the vacuum equation for this five-dimensional space delivers for you both the equation for electromagnetism and this coupling between the Ricci tensor in 4 dimensions and the electromagnetic field. So anyway, the key point for me is to say that looking at such situations in which you have a certain geometric space which projects onto another space, and then you want to understand the geometry, I'm thinking then either Riemannian or Lagrangian geometry, connecting the geometry of the two spaces, actually is a very important, has led to very important developments in geometry. And it happened very late, because it's quite remarkable. We know in mathematics that sub-objects and quotients of objects should always be looked at in a very systematic way. But it seems that geometers have been, of course, looking a lot at submanifolds or hypersurfaces. And it took them a long, long time to think of projections, that is, to look at how you relate the geometry of a total space to the geometry of a base space. Of course, for this you need the notion of bundle, which came only later in mathematics, but this quotient notion could have been there much earlier. And clearly, In the case of Kallu, he was able to conduct this calculation very early on and without any trouble. And it took, as I said, almost 50 years for geometers to really take that seriously. But later on, it has led to many, many important developments. It's very remarkable that this revival of this theory by mathematicians themselves correspond more or less at the moment where the physicists wanted also this bundle theory to be extended because they wanted to have Kallu-Klein theory with not a line added, but a very general homogeneous space because they were looking at much more sophisticated invariance groups than the U1 group, which goes with electromagnetism. They wanted to look at other kinds of interaction, and that was the second revival of Kallu-Klein theory. Anyway, so I wanted to bring this up to show, in this case, that again, the imagination of physicists to deal with very specific problem, which is an obsession, I'm sure for many of you, which is the unification of physics, actually leads to the study of very interesting mathematical structures, even when mathematicians actually have not yet completely grasped this, and I found that useful. So now let me talk a little bit about Cornelius Langsos, of course, a very distinguished relativist, and his theory of generalized Lagrangians. So actually, in the middle of the 19th century, it was known to mathematicians in many different ways that if you look at the total scalar curvature for on the space of metrics or Riemannian metrics on the surface, M is actually a constant. Actually, the formula is the very well-known Gauss-Bonnet formula, contribution both by Gauss and Bonnet. That is, if you integrate the scalar curvature against the volume element of the metric, then on the compact surface, then you get 2 pi times the Euler characteristic. So it shows that the left-hand side is constant, doesn't depend on the metric. And so now, of course, in general relativity, you look at the total scalar curvature in a 4-dimensional space, so it's a different theory. And actually, it's very interesting because that's something which is sometimes not mentioned. The fact that in 2 dimensions you have this invariance is reflected in higher dimensions in some other properties. So, of course, the functional total scalar curvature is a functional. That is, it varies. When you change the metric, you change the values. But still, if you look at its differential on the space of metrics, if you look at its variation on the space of metrics, it keeps some remainder of this invariance in 2 dimensions, and namely the fact that if you look at the variation of this functional, you see a priori the scalar curvature involves second-order derivatives of the metric. So you would expect that the Euler-Lagrange equation, I mean the differential of this functional, should involve 4th-order derivatives, because the usual way things go is that you integrate twice by part the variation, and then you should get a 4th-order equation. But the Einstein equation, which really reflects the variation of this functional, is not 4th-order, it's 2nd-order. And the fact it's 2nd-order is exactly inherited from the invariance in 2 dimensions of this. So this is something to keep in mind. Anyway, so coming to Langsos, in the late 30s, he was, at that time, the number of people thought that maybe, this initial guess of Lagrangian as the total scalar curvature, which had been fantastically successful, maybe was not enough, and one should look at potentially perturbation of the usual Lagrangian, total scalar curvature, by generalized Lagrangians, and then he looked at quantities involving the curvature, which could be done. So as it was very well explained by Hilbert in his discussion about the total scalar curvature, it was, in a sense, it was taking the only scalar expression that you get, which is, in some sense, linear in the curvature. So, of course, the next stage should be to look at quadratic quantities involving curvature. So then if you look a little bit carefully, there are basically only 3 quadratic forms which are natural on the space of curvature tensors. And therefore, you can look at all Lagrangians which just put different weights on the different quadratic forms. So one of the quadratic forms is norm squared of the full curvature tensor. The other one is the norm squared of the Ricci tensor, and the other one is the square of the scalar curvature. So that's a possible basis for the three-dimensional space of invariant quadratic forms on the space of curvature tensors. We can formulate others, but this one is very useful. And it's interesting that in his paper, he noticed if you choose alpha, beta, gamma carefully, then you're in trouble from the physical point of view, because for some choice of alpha, beta, gamma, if you look at the Euler equation, it vanishes. It's identically zero. And so it says it's a very bad choice. And of course, from a mathematical, so his conclusion was this Lagrangian with the very specific choices of alpha, beta, gamma is not an interesting Lagrangian because it has no variation. Of course, from a mathematical point of view, it's fantastic because you have actually found a new invariant because a new quantity which is independent of the metric. And getting such invariants is, of course, always a big feat because you are always looking for invariants. And of course, it generalizes to 4-dimension what had been done in the 19th century with the Gauss-Bonnet theorem for surfaces. So going from dimension 2 to dimension 4. It's very remarkable that, so actually here I wrote the coefficients. So the coefficients are 1, minus 1/4, and 1. And actually the formula which goes with this is actually it's 8 pi squared. Remember it was 2 pi for 2 dimensions, and times the Euler characteristic. What is really very remarkable is that in the same volume of the Annals of Mathematics, it was published in Annals of Mathematics, there's an article by Chern on something else, but and you know that it's in 1944, Chern published again in Annals of Mathematics is well, a groundbreaking article on a new proof of the Gauss-Bonnet theorem. And of course, it's interesting to have a new proof of the Gauss-Bonnet theorem, but of course, what is very important, it opens the door to the theory of characteristic classes. And of course, in his case, it's interesting to see also that, as Chern says always, going to the bundle of frame changed the whole perspective, and that's the way you should think of this. So here again, using ideas of Kallu-Klein theory actually helps you to solve the problem. And what is very remarkable is actually this generalized the whole dimension. So in dimension 6, you should look at cubic expression in the curvature to get an invariant and so on and so forth. It's very interesting that Chern didn't know of the article of Langsos, so I was very pleased to tell him that actually somebody had found this integral before him, but it remained unnoticed. Anyway, so that's a typical missed opportunity because clearly some people should have picked up at the time of Langsos this feature that he had put his fingers on something very interesting from a mathematical point of view. But this didn't happen. I mean, it took the cleverness of Chern to really do this on a completely different basis. So now, let me move on to ADM, Arnold-Desem-Misner approach, which Professor Wold has been using this morning. And so, as you know, I mean, it is one possible way of approaching the study of the Einstein equation. Actually, Yvonne Bruat was the first one to look at it. So instead of thinking, which is look like the right way of looking at things, at the Einstein equation as an equation in a 4-dimensional space for a Lorentzian metric, actually a possible description of the situation, which is the whole idea of Arnold-Desem-Misner, is to think of it to decompose space-time into really a foliation by space hypersurfaces, and which I call sigma here, and of course sigma t. You will have you decompose locally the 4-dimensional space-time into 3-dimensional object times some interval. And then to decompose the metric, you need that to really give full description of the 4-dimensional metric into a curve of 3 objects. One object is a metric induced on the hypersurface, GT. Second object is the second fundamental form of this hypersurface sitting in the 4-dimensional space, which I call KT. And then the last one is a function, very often called the lapse function, And you can always reduce the description, if you choose properly the foliation, to these three curves: a curve of metric, a curve of bilinear forms, and a curve of function. And of course, the key element is to describe the equation for the Einstein equation, the four-dimensional Einstein equation, in this context. So this is what you can do. So the first equation basically describes more or less what I said about the fact that KT was the second fundamental form. And of course, the key equation is the derivative of the second fundamental form is related to all the other fields. And of course, this is not enough. You have also some so-called constraint equations, which actually are very important. And why are they called constraint equations? Just because if you satisfy the first evolution equation, and if you start from an hypersurface where the constraint equations are satisfied, then they continue to be satisfied later on. So they are really constraints. Anyway, so this is the ADM formulation of the Einstein equation, which you all know about. And of course, my point is it really suggests very strongly that the primary object should be to study the space of Riemannian metrics on a manifold, which I call Riemannian of sigma. For me, the object which will be a Riemannian, of course, is a three-dimensional space, not the four-dimensional space, and which for some time relativists called the superspace. After that came into play supersymmetry and things like this, so superspace could be something different. Anyway, so, and of course, the total scalar curvature is a function on the space, which is the space of Lorentzian metric on the space-time M. So we have to play with these two objects. And of course, the Einstein equation, which are the Euler-Lagrange equation of the Lagrangian, the total scalar curvature, express the vanishing of the differential. By the way, it's interesting to see that the vanishing of the gradient of the function using a metric on the space of Lorentzian metric on M. Actually, the space of Lorentzian metric, in the same way as the space of Riemannian metric on the manifold, have a very natural metric. Particularly, there is one which has been playing a quite important role in the, if you look at the theory, I mean, the Hamiltonian approach to the theory of the Einstein equation, which actually was mentioned by Professor Wald, is very, I mean, the ADM approach helps you to think in these terms. And so this Bryce-DeWitt natural pseudo-Riemannian metric on the space of Lorentzian metric plays a role. And using this approach, for example, the fundamental conservation law, which says that the codifferential of Ricci is minus 1/2 the differential of the scalar curvature, which ensures you that the T, the stress energy tensor is conservative, is exactly expressing the fact that the gradient of the scalar curvature, of the total scalar curvature, which is, as I mentioned, the Einstein tensor, lies perpendicularly to the space of, to the orbit under the group of diffeomorphism of the four-dimensional space-time. And this fact is purely trivial because was mentioned also by Professor Wald. That's the equivariance of everything under the group of diffeomorphism. And this, of course, is reflected in the fact that the total scalar curvature is, of course, invariant under change by diffeomorphism. So it shows that this space, I mean, Lorentzian space of, on the space-time or the space of Riemannian metrics are very natural objects to consider and to discuss a number of questions concerning general relativity. Anyway, so now the key point I want to make is that if you go back to the formulation of the ADM, of the Einstein equation in the ADM setting, then actually you can look at just putting a number of things together and using a normalization with more or less phi equal 1, then you can look at this equation in the following way. Actually, they are saying, if you remember what I proposed as evolution equation, that the second derivative of the induced metric on the hypersurface is minus Ricci plus some extra terms. And these extra terms involve only the first derivative in the metric. So in a sense, it suggests that you should look at differential equations involving the Ricci curvature on the space of Riemannian metric on the space-like hypersurfaces. And of course, it's kind of interesting because this is a differential equation in which the second derivative of the curve of metric is Ricci. Actually, the first person who thought about deforming the metric in direction of Ricci, I think, is Thierry Aubin in a paper in 1970. And there's a basic equation I will recall in a minute, which really says that deforming the metric in the direction of its Ricci curvature actually improves the curvature. I'm talking now really in a Riemannian setting. I'm really looking at things on the space-time hypersurfaces. The key formula is the following one. If you take the scalar curvature of the curve of metric G minus T times Ricci, then you get Ricci squared minus 1/2 the Laplacian of the scalar curvature. So typically, if you have a metric which has constant scalar curvature, by deforming the metric in the direction of the Ricci curvature, actually opposite direction, then actually you improve because the scalar curvature is increased by the norm squared of Ricci. Actually, in my thesis, I use this to show that if a manifold has a Ricci equals scalar curvature 0 metric, and you know for topological reasons, for example, it has no metric of positive scalar curvature, actually its Ricci curvature is identically 0, just playing with this formula, because it shows that if Ricci is not 0, you can always get positive scalar curvature, and this is... Anyway, but now the key point is very natural, of course, looking at the Einstein equation, you should look at the second derivative of the metric, but of course it's much more natural, as Thierry Aubin started to do, to deform things in the first order, that is, take curves in which the first derivative is Ricci, not the second. And of course it suggests very much to study the Ricci flow equation, and which of course has been, as you know, a very great development. I think the first occurrence of a question on the Ricci flow is a lecture I gave in 1979 in Berlin, and that's a very specific question, 324 in my list of questions at the end of my lecture, in which I suggest to study the flow. Of course, it's a non-trivial question because, as you know, the Ricci flow, existence of a local flow for a vector field in infinite dimension is by no means a trivial question, because the Ricci curvature, as you know, is an expression in the second derivatives of the metric, which is quite elaborate. And actually, for very, very fundamental reasons, it is, from the analytical point of view, a degenerate equation. Namely, if you look at the principal symbol, you will see that it has characteristic directions in every direction. So it's a very, and of course, it just reflects the invariance under diffeomorphism. So there is always this naturality from the geometric point of view, which is there, but analytically, it's a very difficult thing. So of course, the breakthrough came from Richard Hamilton, Dennis de Turk, who showed that actually you can solve this flow, at least locally. And later on, it went on with a beautiful work by Hamilton, showing that not only you have local flow, but actually if you make some geometric assumptions, you can ensure that actually the flows go up to the end. And this is the way he proved that a manifold which has positive Ricci curvature in 3 dimensions, for example, actually has to be a sphere topologically, because you can converge to actually the round sphere. And many other theorems have been obtained in this spirit. But of course, as you know, it went even further. Of course, the geometric assumptions that Hamilton used, of course, they were very natural if you want to show the flow is global. But then Grisham-Perelman came with further ideas saying that, okay, maybe you have singularities if you don't make these assumptions. But then if you make these assumptions, actually you can still go beyond the singularities. And if you follow very closely what happens at the singularity, you can actually really continue to converge. The key element is to make sure that you have only finitely many singularities. And if your control of the changes you have to make to the topology of the manifold is correctly done, you can still prove the Poincaré conjecture. So it was clearly a fantastic input, which definitely was inspired by general relativity in some way. And of course, there are many other applications of Ricci flow on many questions in geometry. So now let me move on to supergravity and killing spinors quickly. Of course, there have been many generalizations of general relativity. One of them, supergravity, has been coming up in the late 70s, early 80s, and disappeared for some time, reappeared again. It's a bit like Kallu's Klein theory. Actually, the whole idea was to try and combine supersymmetry with the general relativity. And actually, the one thing which was very remarkable was, many articles by many different people showing that for such a theory, dimension 11 is playing a very significant role. It was large enough to do something and small enough to do other things. And of course, if you think of 7 as 7 of 11 as 7 plus 4, 4 for space-time and 7 for some internal geometry, then you are hitting some very, very deep and interesting geometry, like special holonomy G2. And typically, one question which came about in these spaces was very specific spinor fields, the so-called killing spinors, satisfying this overdetermined equation, which in the existence of non-trivial solution to the, so psi is a spinor field, to this equation actually ensures that the metric is Einstein, as one says, that the Ricci is a multiple of the metric, but it has many other properties. It's very remarkable that the first place where this occurred was a paper by Martin Walker and Roger Penrose on actually looking at integrating the geodesic flow of the Kerr metric. And they showed that the number of results which had been obtained by Carter actually could be explained in a much more systematic way, introducing these objects. Anyway, so again, the study of spaces and netting non-trivial killing fields has been really very interesting stimulus in geometry altogether. And in particular, there were beautiful construction by Christian Baer, who showed that these spaces, which were studied by physicists very intensely, finally were quite simple objects. And actually, you can really show that you can build a cone on them in a very natural way, and on which there is a parallel spinor. So a parallel spinor means automatically you have reduced holonomy, and which means you can go back to usual classification. Anyway, I'm coming to my conclusions. So my concluding remarks were, of course, the whole purpose was to show that general relativity has triggered a number of very interesting studies by geometers, providing them with new tools and pushing them to look at new objects which they had not considered before or not seriously enough. It has really led to a completely new viewpoint on the Ricci curvature, which started as a marginal object to become a very central object in geometry. And it also suggested something which has proved to be a fantastic tool, the Ricci flow, and also to missed opportunities. I could have listed a few others. One thing I didn't say, for example, which has been very important, has been the study of space-times, which tend naturally to be non-compact, has really triggered for mathematicians study of asymptotic behaviors in many different ways. Also triggered the new development in conformal geometry by Lichnerowitz, looking at the ADM approach, many other things which I could have mentioned. And again, more deeply, actually, the system of nonlinear partial differential equation with this very specific analytical degeneracy, which is connected to the geometric nature of the equation, has really posed tremendous challenges for solving this system. But I'm sure the real experts will be talking about this. So I'm sure this will be quite a large part of contribution to this conference. Thank you very much.
Thank you very much for this fascinating history. You should please wait to get the microphone if you want to ask questions, please. Because there is another room where the questions would be transmitted. Yeah.
Maybe a question and a remark. The question is, you mentioned Kaluza, And you mentioned the Kallu-Klein theory several times. What was the contribution of Oskar Klein? Was it very important?
Well, the contribution is very clear. Klein came later, in the late 20s. The way he presented the Kallu theory, the extra parameter was a line. But then Klein was contributing in the context of the birth of quantum mechanics. And then there was a question of quantification which came. So, and to do that, you have to replace the line by a circle. And of course, the twist, I mean, the number of twists along the circle is going to give you a charge, which is very directly related to the quantification of charge. So Klein came definitely much later. So in the context I've described, it's correct to call it a Kallu theory, not Kallu-Klein.
And maybe to add one more item to the list of important developments that were triggered by general relativity, I should mention both Noether's theorems, because she explicitly
of course.
started from a problem in general
Absolutely.
relativity.
No.
So I'm adding
Noether's, I mean, all these conserved quantities play a very important role in many different parts of physics, but in particular in general relativity. And Noether's theorem has been formulated full generality, actually, in connection with this. So, thank you.
Yeah, I was quite impressed by this quotation from this Clifford's note. So could Einstein have known about this note?
I don't know. Maybe some experts here know that. I read a number of biographies of Einstein. I never saw it mentioned, but I don't know. Does somebody know? Clifford was really extraordinary. I mean, I've read quite extensively Clifford. I mean, a number of things he has just immediately the right approach. I mean, it's fascinating. You know, we have only 2 minutes left. I'm sorry to...
So maybe one more question.
Well, just a brief comment. You mentioned that the original purpose of Ricci to introduce the Ricci tensor to define preferred directions was not used later on. That's not exactly true. So that idea came back with the Weil tensor, with the preferred directions respect to Weil. And that's used in the Cartan-Karlhede algorithm for local classification of Riemannian metrics. And for conformally flat cases, they also use the Ricci directions.
Okay, thank you. So I should correct my statement. It was too absolute. Thank you very much.
So, thank you.